Okay, welcome back everybody. Do you have questions? No questions? So it means that either everything is clear, either nothing is clear. You should have plenty of questions by now, because we have seen, well, a big deal. I mean, a few things we already seen, and there should be questions. You should have spotted some errors in the slides, for example. Usually at this time of the lecture, there's always somebody excuse me, but on line 2 of slide number, I don't tell you what is the slide, there is this mistake. And I say, oh yes, oh, really? Every year. So, nobody has spotted anything? So, I think you will have difficult holidays then, because you will have to study everything during your holidays, Christmas holidays. Well, it's your choice. Okay. Well, last time that we met, we started talking about curves and surfaces, and we were dealing with the problem of representing curves in a smart, viable way that we could use in our graphics programs. So we were starting exploring what to do, and we were discussing the concept of parametric continuity. So main idea, if you remember, was that we could, in theory, represent the curves with parametric equations, with parameters, for example, u and v. We made some examples. We are aware that in this way there are some set of curves that we cannot represent, for example, circles. But if we forget for the moment about circles, it seems a viable solution. However, if our idea is to stitch together simple curves in order to obtain a complex one, what is called a compound curve, then we have to face at least one problem, which is to guarantee that we have continuity at the joint points. Hello. And one of such continuity that we define is called parametric continuity. We defined it at the joint point, and we defined a class of continuity based on the concept of the derivative of the parametric functions which are defining each curve. Do you remember that? We stopped right here when I was about to make you notice that a big problem that we have with such line of reasoning is that we are actually dependent from the way in which we parameterize the curve. That is, not only we have problem in keeping curves smoothly joined, but also with this line of reasoning we have to take care of how we parameterize the curve. Otherwise, even the way we choose parameterization has an effect on the continuity. Consider the following example. That seems a simple enough example. It's two curves, well, it's actually two lines, but they can be considered in general as curves, which have a joint point in B. So these are the two parameter equations. There are two rays. One ray is starting on A, the other ray is starting on B, and this is the direction vector of the ray. I'm stitching the two rays at the B point in such a way that the two rays are collinear. We can check, of course, is C0 continuous in the joint point by construction? Is it C1 continuous by our definition? We have to take the first derivative of each one of the two parametric equations. And it turns out that this is the equation for the first derivative, and this is the equation for the first derivative of the other equation for g. And you can see that in general, actually, they're not equal, because one is b minus a, the other one is c minus b. So even if, in this specific case, these are two direction vectors, b minus a and c minus b, you see, those are 2 point vectors. You make the difference between them, you obtain one vector which is one direction vector. This is not the same vector because they have the same direction, but in general you cannot guarantee that they have the same norm, right? It depends from b, from a, from c. So they are not in general C1 continuous. If you want to have a warranty of parametric continuity in general for such a geometrical disposition, then you have to parameterize in a different way. Namely, you could redefine the two functions going through a normalization of the direction vector like this. So this is the direction vector, but I apply a division for the norm of the same direction vector. So I am sure that when I go to the first derivative of these two guys over here, both of them at the first derivative are always equal to 1. Well, are always equal to a norm vector. Well, a norm vector with a unit length. And therefore, I would say that they are both of them in the same vector because they have the same direction and they have the same norm, which is 1. Because by definition, I construct them in a way to bring them to unit length. So you have to reparameterize the curve segment if you cannot guarantee in general C1 continuity, C2 continuity, C3 continuity. This can become cumbersome. I mean, difficult to do. So we could relax our definition at this point, and instead of requiring from a compound curve at every joint node, instead of requiring parametric continuity, we could relax our requirements and ask for geometric continuity. What is geometric continuity? Well, you have geometric continuity here. The idea is basically that you don't require a strict equalness, but just a general proportionality. Like, for example, here, the problem is you have two vectors, two direction vectors here. You are sure, because they're collinear by construction, that they have the same direction, but you're not sure about their length. And this prevents you from having a general parametric continuity. But geometrically, they make sense. It's only your definition that is too strict. So we could relax that and creating, instead of a C class, which is the class of parametric continuity, a G class, which is a class of geometric continuity, in which I just require, so to say, the direction of the vector to be the same, but not its unit length. Well, its length. How do I represent that? Well, I just require general proportionality, like, for example, a vector which is 1, 1, 1, and a vector which is 2, 2, 2, exhibits general proportionality, so it's the same direction vector, but with different norm. So in general, GK continuity class can be obtained. The two curves are CK minus 1, so I require parametric continuity at the prior class and geometrical continuity at the considered class. This is what I could ask for, and I define this as geometric continuity. So this is actually what happens here in my example, in which I have parametric continuity at class 0 and geometric continuity of class 1. Then the other problem I have is, but you knew that already from the geometry you had during your early years at university, that with such parametric curves, in general, you cannot represent, they're not simply powerful enough to represent some sets, some families of curves. Like, for example, circles or ellipses. You cannot do them with a set of parametric equations. You cannot represent them unless you use a fourth coordinate. So you use a parametric representation with a fourth coordinate, a homogeneous coordinate. This category of curves, using also homogeneous coordinates, they are called rational curves. With the rational curves, you can use the additional parameter to add the complexity you need to describe circles and hyperboles and ellipses. So, okay, that's a little bit the background that I wanted to lay down before starting describing how Bezier curves and B-splines actually work. So we have a problem, as I told you last time in computer graphics, that we need an immediate way to handle curves without knowing a priori their equation. Actually, we're not interested, our user is not interested in the equation, in the real algebraic equation of the curve. And basically, we as programmers would rather not be interested in the real equation underneath the curve. So it would be very nice if I could express any curve I want with a set of parameters which are not mathematically related to the problem, but they are related to the problem in a geometrical way. By geometrical, I mean, and you know what I mean because probably you have already used in at least once in your life Bezier curves. I would like to define a curve by just setting some points, which are called control points, along which my curve is bound to pass. What are the mechanisms that allow me to do this? Well, these are some requirements. So I need something which is intuitive to use, flexible, invariant. I mean, I fix the anchor points. I have a curve calculated from these anchor points. If I transform the anchor points, I want the curve to stay the same. I mean, imagine translating, I define a curve with a set of 4 anchor points. Then I apply a translation with a displacement vector across my plane. I want the curve to look the same, only shifted by the displacement vector. So I need a system which guarantees me affinity on the transformation. Hello. And I need a way which is not too complex numerically. So efficiency and numerically stable. Basically, there are 3 types of curves that we use now in computer graphics. The first class, which is the most specific, I mean the less general, is the Bezier curves. Then you have an extension of Bezier curves, which is B-splines. Then you have a further extension of B-splines, which is called NURBS. By construction, you can create a B-spline in a way that it is a Bezier curve. I mean, Bezier is a subset of B-splines. You can create a NURBS curve in a way that it looks like a B-spline. I mean, B-splines are a subset of NURBS. NURBS are the most general curve in the whole. NURBS stands for non-uniform, rational B-splines. So B-splines mean that they are B-splines, but they are rational. It means that they use a fourth homogeneous coordinate, so they allow you to solve the circle, hyperboles, ellipses problem. And non-uniform is because they relax a limitation of the B-splines that we will see. So they are the most general. If I am not wrong, what you can do in OpenGL is that you can program a Bezier curve, and you have what they call the so-called Bezier evaluators, and you can control a NURBS curve. You can do simply B-spline, because if you have NURBS in your hand, then you also have B-splines. However, Bezier is given to you because they are a little bit simpler. There are a lot less parameters to specify. So if you don't need the refinement of a NURBS, you can go for a Bezier, and it's much easier to set up the evaluator for drawing a Bezier. So that's why they give you the plain vanilla version, well, the simpler version, which is Bezier, or you have the full power of the theory with the NURBS. What are the advantages of these curves? You have the control point system at your hand, so the user can define the control points. The curve is drawn not really to intersect, but to follow in some way the control points the user decides. If a user changes the position of a control point, the shape of the curve follows in a consistent fashion. You don't need to manipulate the equation to change the curve as a programmer. You can add control points without changing the shape of the curve. This is an operation which is called, hello, flying in or flying out? Training, I mean going by train. That's good. So you can have what is called in curve terms a degree manipulation. You can add more control points to the curve without changing the shape of the curve. And we will see that that's a good thing when you want to have additional flexibility localized to a specific area of your curve. So you need more control points in that area. You can add control points without changing the curve. There are mathematical techniques to do that. That's quite cool. For those of you who get excited about these things, but, well. They are very geometric. I mean, everything that we will do has very neat, very direct geometrical meaning. So it's very easy to understand what you're going to do. And once you know how the curves work, you just add one dimension and you go to surfaces. So it's very easy to extend this concept from a curve in 3D to a surface in 3D. Just by adding, well, duplicating the set of equations. It's kind of straightforward. Okay, this one I told you. This one I told you, it's a representation as a picture of each category of curves, the subset of the previous one. So let's start with the most simple, which is the Bezier curve. This is the general expression of a Bezier curve. CDU, C is the curve, U is the parameter running along the curve. Usually we make the parameter run from 0 to 1. 0 being the first point on the Bezier curve, 1 being the end point of the Bezier curve. The idea is that I have a set of n plus 1 control points, which are called P. So this P is actually containing xi, yi, zi, right? And 1 as the fourth coordinate, because they're points. And you see, well, please note, this is, well, it's easy now, but as soon as we will be starting fiddling around with parameters, it will start to get a little bit confusing. If you don't remember that, if you have this set of anchor points, control points, from P0 to Pn, this is actually n plus 1 control points that you have. Okay? because it's a, well, technically speaking, it's a zero-based array. And zero-based array going from 0 to n has n plus 1 elements, right? You should know because you're programmers. So these are n plus 1 points from P0 to Pn. The curve is expressed as the weighted sum of all the control points of where the control point plays the role of the weight, and there is a coefficient which is calculated from a specific formula which is called the Bernstein polynomial. This is not something that Bézier invented. This was something that was already there, and Pierre Bézier selected as fit for his purposes. Why? Because, well, apart from the definition which is here for the sake of completeness, so you just have a taste of how it works, namely you see that it's dependent from the degree of the curve, which is n. The degree of the curve depends on the number of control points minus 1. So you have, if you have with 4 control points, you have a degree 3 curve, right? And I, so this is the degree that you need, and I is the specific Bernstein polynomial that you need. So basically, if you have 4 control points, you will go from 0 to n with n3, and you will need B30, B31, B32, and B33. But plugging in here always 3, and here, every time you do the sum, 0, 1, 2, 3. How do this Bernstein polynomial look like? Look at this example. This example is actually 1 degree more. So this is a degree 4 curve, because I have 5 control points. You can see them over here. This is P0, P1, P2, P3, P4. They form an inscription polygon in which the curve will always live. So your curve will not be passing through the control points. It will never pass through them. But it will always be inside the polygon formed by the control points. This is called the control polygon. So your curve is always inside the control polygon. And as you can see, it is traced as a weighted average of the control points with the Bernstein polynomials. How do they work? They work according to a principle which is called partition of unity. Partition of unity means that at every value of your parameter, which is u, running from 0 to 1, this is your parameter. So this is actually c of 0 over here, and this is the first point of your curve. And at the end of the curve, you have c with u equals to 1, c of 1, right, at the end of the curve. All the values of u in between are used to plot, to draw the curve. Like here, for example, you see u equals to 0.5 actually corresponds to this point on the curve. This is the value of the parameter. This is c of 0.5, this point on the curve here. Well, back to partition of unity. For every value of u, going from 0, which is over here, to 1, which is over here, the sum of all the Bernstein polynomials which are involved in the weighted formula, so this sum over here, the sum of all the Bernstein polynomial. So in a case of a 4-degree curve, so 5 control points, B40, B41, B42, B43, and B44, sum together, they always give you 1. So that's why it's called partition of unity. Why? Because by definition of Bernstein, then you have that the first Bernstein polynomial, B40, at 0 equals to 0. All the other Bernstein polynomial equal to 0, except the highest degree Bernstein polynomial, which equals to 1 over here. So what happens? That the only survivor over here at 0 I'm sorry, this is 0, this is 1, and this is the value of u. U here, the value of u here is 0, the value of u here is 1. In fact, you see that here, at P0, B40 equals to 1, all the others equal to 0, right? So what happens? That in your definition over here, all the coordinates of this are all nilled, except the first one, when u equals to 0. So when u equals to 0, this Bernstein is 1 when p equals to 0. So c of 0 equals to p0. All the other ones are nullified by the Bernstein polynomial, you see? So it actually happens that c in u equals to 0 coincides with p0. You see? The same thing on the other side. Here u equals to 1. It means that all other Bernstein polynomials, except the last one, will be 0. So it means that P4, which is the last one of the 5 control points, is the only one surviving, because all the other B's are equals to 0, except B44, which is the last one. So C with u equals to 1 will be equal to B44, which equals to 1, P4, which is the last control point. So this actually tells you that the curve starts on the first control point, ends on the second control point. What happens in between? In between there is a mixed situation. It is not so clear like in the beginning and in the end. You see here in this graph how more or less is the mix. Here B40, B41, B42, B43 and B44 actually add a contribution, mixing together P0, P1, P2, P3, P4. You can see that as long as my parameter is in the beginning, you have a prevalence. Well, the position of P0 and P1 matters more than the position of P3 and P4. Because look, with U, which is at the beginning here, the most prominent contribution is given by B40 and B41. So the position of P0 and P1 are the most significant for determining the position of the curve. The position of P3 and P4 here, P3 is the green one here, and P4 is the blue one here, it's almost irrelevant. I mean, it's not relevant actually, because it's near to 0 here, the value of B. You see what I mean? So even if I were actually moving P3 or P4, I am not moving much. I am not moving much, this part. I am moving anyhow, because you see I have some small contribution. Because in generally, ideally speaking, the only position in which I have no contribution from the other polynomials is really u equals to 0. As soon as u is not equal to 0, I have increasing contribution from the others. But there is always a kind of contribution. But, of course, I have a bigger contribution from P0, P1, bigger than the contribution from P3, P4. The opposite happens on the other side of the curve. Here, what matters most for the curve is the position of P4 and P3 over here. Because of the position contribution of the Bernstein polynomial when u is near to 1 over here. So actually, do you see how it works? The coordinates of the control points act as weights. And the Bernstein polynomials are partitioner of unity, which give more or less power to the position of the control point. It's brilliant because it's extremely simple. This is something that already existed. Barbieri just took it and used it to create a weighted curve inside the control polygon. Okay. What are the most important properties of such a curve? Well, one I already told you, definition of the degree of a Bezier curve. If I have n plus 1 control points, like in my example, 5 control points, it means that the degree of the curve is 4. So with 5 control points, a 4-degree curve. This is easy to understand if you look at the definition of the Bernstein polynomial. In the definition of the Bernstein polynomial, you have a polynomial which at its most is n minus 0, because I starts from 0. So the highest degree of the polynomial representing the curve is n. So the general degree of the curve is n. Cu always passes through P0 and Pn, as I already demonstrated to you. Just because the Bernstein polynomial nullifies and unifies in the first and in the last control point. Non-negativity, the function is always positive, and there is the principle of partition of unity. So the sum of all the Bernstein polynomials for every value of the parameter u always gives 1. This concept is the foundation of the working principle of the Bezier curve. So, since all basis functions are in the range of 0 and 1, and sum to 1, they can be considered as weights in the computation of a weighted average. More precisely, we could say, to compute C of u, one takes the weight Bni of u for the control point Pi and sum them together. This is, in words, is the working principle of a Bezier curve. Good. What happens when I move one of the control points? This is a mathematical representation of this situation. You have, well, given Cu as the original curve, the new curve that you obtain by moving one of the control points can be expressed as, well, imagine that you're moving control point number k, with k, which is somehow between P0 and Pn. Then you could say that the first part of the curve, from control point 0 to control point Pk minus 1, is not involved, because you don't move, those control points stay the same, so that part of the polynomial stays the same as well. What the part of polynomial that changes is the monomial of the degree related to the control point you're choosing. So, of degree k minus 1 here. So, bnk u pk plus v. pk is the original position of the control point. V is your displacement vector. That is the vector that represents the movement that you performed on your control point, displacement vector. And then, of course, there are the other control points that you didn't change, so they stay the same as in the previous curve. So you can factorize everything. If you factorize, it turns out that you have, well, the normal, well, the original curve made up of, you see, it's actually here, bnk multiplied by pk plus bnk multiplied by v. You can just solve down this part and get back this bk to where it belongs. This allows you to write that the new curve is actually like the old curve, cu, plus the displacement vector weighted by the Bernstein polynomial of the degree related to the control point you have moved. But this Bernstein polynomial is 0 only either here or here. And it is not 0, well, actually, well, yes, either here or here, and it is non-zero everywhere else. Since it is non-zero everywhere else, it means that the change to the original curve is more or less global for the whole curve. So every point in your curve actually changes a little bit. The change that you make to your curve, you see an example here, is not actually impacting only the immediate vicinity of your curve. It's actually changing in a bigger or smaller way the entirety of your curve. You see in this example, I am moving this point from here to here. This has a bigger effect in the vicinity of the curve, but actually you have changes also in parts of the curve which are rather far from the control point that I have chosen. So Bezier curves are good, but since Bernstein polynomial work as a partition of unity and they are in general non-zero everywhere in the whole range of the parameter, you cannot localize the effect of moving a control point. If you move a control point, you change the entire curve. What you don't change is the fact that the curve still starts from P0 and still ends in P1. Because that's an effect of the fact that the minimum degree Bernstein polynomial is like this, and the maximum degree Bernstein polynomial is like that. So that doesn't change. But all the intermediate degree Bernstein polynomials are always non-zero in their whole parameter range. And this prevents you from making local modification to the curve. When you change a Bezier curve, when you change a control point in a Bezier curve, you change the whole curve. Because your polynomials are always non-zero in a whole parameter range. Is that clear? Right. This is good, this is bad. Well, it's not as bad as it sounds. Well, here we have a situation, look. This situation over here is we have 9 control points. We are going up to P8, so it's 9 control points. The effect of this thing over here is moving control point number 3 from this position to this position over here. See? So by performing this displacement vector, this is the change that I get. Well, it's not actually very intuitive, right? I mean, it does make a change. But with so many points, it starts getting difficult to actually know beforehand which kind of movement or what control point I should take or I should move to get the effect I want. So it's not very intuitive. But why is that? Because this specific Bezier curve has a very high degree. And the higher the degree, the less intuitive is the effect, the general effect I have on the curve. It is so true that I will get back to this later. That's the degree elevation method. When you use high degree Bezier, like for example, this is a 10 degree. Yes. And it starts to get difficult to move the control points to obtain what I want. So we get back to the earlier problem. We would like to create simpler, with a less degree, Bezier curves and join them, making a compound curve and creating compound Beziers. In this way, I could have a better control on the localization when I move control points, because I'm using a shorter Bezier curve. So when I move a control point, I have a more geometrically related response. Right? You follow me? The idea is, with a very high degree curve, like for example this one, to get the change I need, it's very difficult to understand which control point to move and of how much I have to move it. Why is that? Because there is a very high degree, so a lot of burst time polynomials in between, and a very spread effect of delocalization of my movement. So it gets difficult. It is easier when I have very low degree Bezier curves. So the idea is, well, let's try to make, instead of making one big high degree curve with a high degree Bezier, let's try to make a compound curve using smaller, well, lower degree Bezier curves. But then we come back to square one. We come back to the problem of guaranteeing geometric continuity in the joint points. This is why the next step is putting on your plate B-splines. B-splines are integrating the idea of creating compound Beziers. That's why you could say that you can simplify a B-spline as a superset of Bezier, because B-spline is actually a compact notation for a compound Bezier. We will see that. Let's step a little back to the thing that in one way you want to try to elevate the degree of your curve in order to have more control points to manipulate. Because the problem, for example, with a low degree Bezier is that you have 3 or 4 control points altogether to move. That would be not enough if you want to get a complex shape. So you want more control points. But on the other hand, if you have a lot of control points, then as soon as you move one of them, all your curve changes dramatically. So it's really hard to find the right balance between flexibility and controllability with the Bezier curves. So you have in theory a degree elevation method, you see, it is this one, in which starting from the control points P0, P1, P2, P3, P4, P5, you can calculate the new set of control points, adding them actually, with this formula. So you elevate the degree, you add control points without changing the curve. And then adding the control point, you have one handle more to do the experiment and do something more. This is a function that if you ever try to use Adobe Illustrator or something like that, you have the pen tool, and if you use the pen tool, you can add an anchor point on a curve that you have already drawn, and actually you simply add this control point and you don't change the curve. That tool here is applying this method over here of elevating the curve. It adds a control point, and then you can use that control point to move the curve and change the curve. But if you try yourself using Adobe Illustrator, you will see. Try with a spline with 3 control points and try to make what you want. Then try elevating the degree, try to make what you want. You will see that the more control points you have, the more hassle, the more difficult is to actually place them correctly, because everything starts moving. So, complex curve shaping. Let's create a system for representing compound Beziers without worrying about G1. G1 being the geometric continuity of class 1. With B-spline, I can create a curve of the same complexity by using a polynomial of a much smaller degree. So this is an example. This is more or less the same shape. You see, over here and over here. For doing this, I need an 11th degree polynomial. It's 12 control points, so it's an 11 degree. I can do more or less the same shape. Instead of using an 11th degree Bezier, I can use, I believe here, 8 control points, so it's a 7th degree polynomial. So I go down of 4 degrees, which is something. So it's flexible, it's localized, and it has a lower degree. And for that reason, when I change the control point here, I still have flexibility, and my changes are more localized to the curve. How do I do that? I do that by starting from the idea of compound Beziers over here. The points in which I would like to join my simple Beziers to form a compound Bezier, actually, I define those points by defining special values of the parameter in which I want to separate the domain of the curve. So I'm not actually saying I want a joint point here. So I don't specify the point on the curve. I specify the separation as a value of u, that is the parameter, because that's easier. So the idea is that I subdivide the parameter space, that is the value of u from 0 to 1, in segments. So it's the originating set of values, the set from 0 to 1 of the parameter, that allows me to describe how I want to segment my curve. Every point I define in the u range, so in the parameter, and which defines a subsegment of the curve, it's called a knot. K-N-O-T, a knot. To every knot, which is a specific value of u, corresponds a point on the curve. But the knot is not the point on the curve. The knot is the value of the parameter which originates the segmentation, right? Look, I think I have a picture here. I have the domain. This domain is the domain of the parameters which is originating the curve. I define splitting my complex curve in simpler curves, like I wanted to do with the Bezier compound curve. But my splitting is defined not on the curve, but earlier in the parameter, in the domain of the parameter here. So these are the knots. So here it will be u equals to 0.2. Here will be u equals to 0.25. Here it will be u equals to, I don't know, whatever, 65. And here u equals to 88. Right? So those are my knots. So these knots, through the equation of the curve, they got projected as points, knot points on the curve. These are the segments in which modifications on the anchor point are localized with a specific criterion that we will see right now. So, basically, first step, when I jump from Bezier curves to B-splines, the idea is I subdivide the curve into smaller segments. These segments are separated by knot points. But the knot points are not defined themselves. They are obtained by the fact that I am actually subdividing the originating parameter domain in knots. So what I have to provide to my B-spline curve is a set of control points, like I did earlier, plus a set of knots, which is the list of subdivisions I want to make on the parameter domain. This is the basic idea of B-splines curve. What do I gain? Look, this is what I can do with a 10-degree Bezier. Okay, this is a B-spline here, you see? I'm sorry, it's a Bezier. It's a 10-degree Bezier with 11 control points. This is what I obtain. As you can see, you have troubles here because, well, it's somehow following your control polyline, but it's not actually very satisfying, right? I mean, it starts to get difficult to be modeled like that way. This is the same control points using the B-spline method. You see that the curve is much more following the control polyline. Now, that's what I call something like a news. You see? You really have much more localized control around each one of the control points. Really? You see? It's really like you feel like you could actually moving one of the control points and having the curve actually following the control point the way you think it should. So you have more flexibility at high degrees. And over here you can see there is the knot points that you need to define in order for the curve to behave like this. So you get the benefit in return from a higher complexity because not only you have to define the control points, but other than the control points, you have to define the knots over here. It's actually like you are defining in one go, in only one equation, 1, 2, 3, 4, 5, 6, 7, 8 Bezier curves stitched together in a compound Bezier. But what you're actually doing is expressing everything in one go as a B-spline with one single equation. But this equation, instead of using only the control points, it also uses another vector, which is the knot points. Right? So one equation, two input vectors, same number of control points, added enhanced flexibility. Is it clear? Good. So these are the knots. So what's the definition? Apparently the definition is the same. Cu is the weighted sum of the points over here along to the parameter, which is u, with another set of polynomials, which is actually not polynomials but functions, function n. The function n is obtained by using a set of formulas which are called the Cox-de Boer formulas over here. This Cox-de Boer formulas. This is the full definition. Given n plus 1 control points from P0 to Pn, and the knot vector, which is defined over the space of the parameters from U0 to Um, the B-spline curve of degree P obtained, defined by this control point and the knot vector U is the following. And the degree of the curve is not related anymore just to the number of control points, but it also depends from the number of knots you are defining. Actually, they are related with this equation. So M, which is the number of knot vectors, has to be N plus 1, which is the number of control points, plus P, which is the degree. Or, in reverse order, the degree of your curve is how many knots you define, minus n, which is actually the number of control points minus 1, minus 1. This is the degree of your curve. What are the main differences between a B-spline and a Bezier? One, that the domain is subdivided by knots, something that in Bezier does not happen. We don't have that concept in Bezier. Two, and that's the real trick, while the Bezier basis function were always non-zero on the entire interval, the basis function of B-spline are not non-zero on the entire interval. So it means that they are zero almost everywhere, except in specific places. Look, a picture is worth a million words. This is the series of Cox-de Boer formula for degree number 0, attached to control point number 1, control point number 2, control point number 3. This is the Cox-de Boer formula for degree 1. And if you could see, but I'm going to draw it for you, the plot of the Cox-de Boer formulas for degree number 2, you would say a curve whose span is actually taking 3 units. Over here, you see, this span is 0 everywhere, except in one span near the control point around which it is related. This is the first level Cox-de Boer formula attached to P0. This is the first level Cox-de Boer formula attached to P1. This is the first level Cox-de Boer formula attached to P2. P being the control point. When you are going to degree 1, you don't have squares anymore, but you elevate this of 1 degree, so your non-zero span actually is bigger, and you have here a span of 2. This is the span for P0 at first level, so it has a span of 2, and P1 at first level. When you go to the second level, you have a curve which is actually spanning for 3 units, starting from 0, 1, 2, etc., etc. And the higher is your recursion formula, the broader is the span in which it is non-zero. But always it has a definite span in which it is non-zero, and in all the other part, it is 0. So the idea is that these functions have the peculiarity that they are they are non-zero in localized areas, in localized ranges of the parameter. For this reason, you see, non-zero range of basis function. If you want to do it generally, the basis function NIP, according to U, is non-zero between Ui and Ui plus P plus 1, P being the degree of the curve. Or equivalently, NIP of U is non-zero on P plus 1 not spans. So from Ui plus 1 to Ui plus P plus 1. So you have it here. I mean, when you're reasoning at level 0, it is 1. When you're reasoning at level 1, you have a span of 2, starting from the knot you are considering over here. What is the effect? The effect is that when you're moving a control point in a B-spline, you are not changing all the curve like happened in the Bezier curve. In the Bezier curve, that happened because the Bernstein polynomials were non-zero over the whole parameter range. But the Cox-de Boer formulas are always non-zero, except in ranges which are localized around the knots. So it really depends on how you have placed the knots over here. They define the spans, well, the areas, the segments on the curve, which will be affected by a displacement of a control point, and the spans which will not be affected by the displacement of a control point. Look, for example, at this example here. You have a rather high degree B-spline. Actually, it's 12 control points. Actually, this does not mean that it is a degree 12 curve, because degree in B-spline does not coincide with number of control point minus 1. Mind that. Eh? What do you need to know? The degree of that curve. You also need to know how many knots you are defining on the curve. So here are the knots over here. You see, this is one knot. This is one knot over here. This is another one. This is another one. And every knot, well, every couple of knots defines a span. A span is a segment on the curve, you see? I'm starting from knot number 4 because this curve is clamped. I'm going to explain that in a moment. But clamped actually means that the curve, you see, starts from the first control point and ends in the last control point. This was a given in Bezier, but it's not a given in B-spline. To obtain this effect in B-spline, we have to configure the knots in a way that we have a number of knots equal to the degree of the curve defined at 0, and the same number of knots equal to the degree of the curve defined at 1. If I do that, then my curve is clamped, meaning that it starts from the first control point and it ends on the last control point. If I use 13 control points like here, and I use 18 knots, so m equals to 17, it means that I have a curve of degree 4. To clamp a curve of degree 4, I need to define the first 4 knots, U0, U1, U2, U3, U4, to 0. And the last 4 knots, U13, U14, U15, U16, U17, to 1. So those knots are blocked because I want to clamp the curve to the beginning and to the end. Which means that from U4 until U13, I am free to decide the position of the knots. Here you have them, from 4 to 13. The position of the knots, these are the values of parameters. These parameters then will map on the curve and give me segments on the curve. So actually the segment 1 of the curve over here is defined from the value of the knots between U4 to U5 here. Span number 2 is defined from U5 to U6 here. Segment number 3 is from the span U6 to U7 and so on. When you're changing the position of a control point, namely here control point number 6, the rule of locality tells you, because of the disposition of the Cox-de-Boer formula, look, you see, this gives you the locality of your displacement. Okay? If you had a curve of degree 1, then your locality will be limited to one span, to one segment. If you had a degree 2 curve, then your locality will be limited to 2 spans. But you have a degree 4 curve, so it means that it is not even the curve, it's even a more complex curve. So you're actually spanning 4 spans. The rule says, where is it? From UI, I being the control point you move, to UI plus P plus 1. So if I apply this rule, I'm moving control point 6. It means that my curve will change from U6 here to U6 plus P. P is 4 because I have a 4-degree curve, plus 1. So until U11, so here, U11. It means that which are the portions of the curve that will change? Portion number 3, 4, 5, 6, and 7 will be affected by the movement of the control point. Portions number 1 and 2 and portion number 8 and 9 will not be affected by the movement of control point 6. And as you can see, the effect of moving P6 from the original curve to the new curve is actually that everything from here, so span number 3, 4, 5, 6, until, well, 7, is changing. You have changes. But these spans over here do not change. So you have attained one of your goals, that is to localize modifications given by moving one control point. And this actually gives you more flexibility, more geometric response to your user. Okay. This slide over here tells you in full how you can define the knot vector in order to have the curve behave as you want. If the knot vector does not have any particular structure, then your generated curve will not touch the first and the last legs of the control polyline, as shown in the left figure below. Left figure below is this one, or below is this one, the left figure below. This type of B-spline is an open B-spline, but usually you want to clamp. So you want really your curve starting and ending there. If you want to do so, the first knot and the last knot must be of multiplicity P plus 1. So you have to repeat 1, 2, 3, 4 times So this is 4 times because you have degree 3. In the case of the other curve, you had a degree 4. So you need 5 times, 1, 2, 3, 4, 5, to repeat the first knot. So this is a must that you need to do. Let's make another example. If you use n plus 1 control points, so 10 control points, so your n is 9. And you want to do a degree 3 curve. Then you need 13 control, then you need M13 because you need 14 knots. Why you need 14 knots? Because you want to clamp, so you need the first 4 knots and the other 4 knots. So it goes to be 4 and 4. And then you need at last 6 other knots to get a degree 3 curve, given that you want to use 9 control points. You see? Then the knots in between, you can decide. For example, you can make a uniform knot distribution, or you can make an unbalanced knot distribution. It depends from the behavior you want to have when moving your curve. Of course, the distribution of your knots in the parameter domain affects the shape of the segments and therefore the behavior of the curve when you're moving on and off the control points. Okay. Beware, you have a pencil here. This means that you are required to understand this example and answer this question. So, for example, in the exam, you could have a picture like this, but different. And you could be asked to say, what is the degree of this curve? Then you know that it is, well, I tell you it's a B-spline. Then you count the control points, you count the knots, you make the calculations. Or I could ask you, what happens if I move B8? Then you have to say, well, it's the B-spline of degree 4, there are so many knots, so the spans are this and this and this. So in this case, the segment does not move because it is outside the area of movement. Or it does move because, okay? So just to show that you more or less understood how it works. Why did I have to insist on this? Because when we will see later that we are going to use the NURB evaluator to draw the curve, OpenGL asks you, please provide me with the control point vector, and then it asks you, please provide me with the knot vector. So it doesn't actually decide from itself how to dispose the knot. It's up to you to provide OpenGL with the knot vector. So you really have to know how many knots you need and what is the value for the knots to have the desired effect. So there is no other way but knowing how the baby here works. If you want to use NURBS, of course. Okay, I would say let's take a 600 seconds break, and I think I would show you after the break a program that some students in earlier courses made in order to show how curves, Bezier curves and NURB curve work. So we will fiddle around a little bit with the values and see their behavior. Shall we start again? You have this small program available for download. I believe it's actually one of the paper clips available as download right into the calendar of the lectures. So one of the paper clips is something like curvestutor.zip. You can download it and you can run it on your own machine, so you can do your own. I think there's the source also, so I can also peep into the source to learn how to use the OpenGL evaluators, which is much the main goal of the lecture, to give you the theory but also the practice. I mean, in the end, you want to draw curves. And to draw curves, you need to know what are the needed parameters. That's why we faced all the theory. And now it's time to see a little bit of practice. And you can see, well, just by reading the source, which is available for download. And this is actually the program running. First of all, to remind you that we are dealing with curves, but this does not mean that we are dealing with a bidimensional problem. It's a curve in 3D. So it's a curve, but the problem is three-dimensional. So don't get tricked by the fact that it is a curve, that this curve is lying on a plane. In general, it is not. For example, you can see this curve right here. Okay. You see that it's not actually lying on a plane. It's a curve with its specificity in 3D. You see? You see it? It's a bit fine, but you clearly see that it's defined as a 3D object. It's a curve, it's not a surface. That is not bidimensional. Okay, so that was important to remember. And actually, you can see here what is the degree of this Bezier curve. Come on, 3, right? 3, because I have 4 control points. This is control point number 1, 2, 3, 4. Unluckily, I cannot drag the control points to modify the curve, but like all Nate Robbins tutorials, I have the availability of controlling, a piece of this simulated piece of the source over here, and I can, with the user interface of Nate Robbins tutorials, okay, this is P0, so you see, even if I move P0, the curve, because it is a Bezier, always remains, so to speak, clamped. This is because of the nature of the Bernstein polynomial, which is used in the Bezier curve. Same thing with P3, which is the 4th point, over here. And of course, I can move intermediate anchor points. With intermediate anchor points, I can modify the curve. Give it another shape. One limitation of this tutorial is that I cannot change the degree of the curve. So one feasible project for any of you who's interested would be to enhance this one, allowing me, for example, to add control points, change the degree of the curve. That also would be nice. So I'm quite limited here. But one nice thing here is that you see the chunk of OpenGL you need in order to visualize the specific code. What you do is that you actually declare the evaluator, which is this one. This is the range of the parameter u. This is the degree of the curve. This is the number of control points you're going to pass. Actually, this should be implicit, but this is the way they provide the API, so we compile. And this is the array of coordinates. Okay, this is draw the vertex, and this is the to build the curve. You have to invoke the evaluator in steps. So the evaluator, you give to evaluator a value of u, of the parameter, and in turn it gives you the position of one coordinate. So if you want to plot the curve, you actually have to simulate the curve by stitching together the points. This is what it does. You see, it's using line strip and actually connecting. It's doing in steps. You see, u equals to 0, u equals to 0.1, u equals, 0.01, u equals 0.02, u equals 0.03, etc., 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 by increments of 100 until 100. So it's actually building the curve by using 100 points, by calling it using 100 different values of u. You can see it very well because if you work on the loop, you actually see that you build it. See? Okay? Clear how it works? This is just because it's actually using u from 0 to 0.16. And here is from 0 to 0.5. Okay, so until the end of the curve. It is done this way to make you remember that u is the parameter and the point is a different thing, which is obtained from it. Okay, you also have the surface. As I told you, one beauty of the theory of the curves, be it Bezier, be it NURBS, is that it is, well, simple to extend the concept to surfaces. What you actually do is just using two evaluators instead of using one evaluator. So it's actually making a grid of curve. One curve using one set of parameters, u, and another curve using another set of parameters, v, and matching them together. Look, this is an example of a surface. This is the control points. So you can actually move the surface the way you want. Right, that's cool. And you can play the same trick. You see, it's actually, you actually build the surface by just mixing together the curves. You can really control the loops, making it finer. Yeah, you see how it works? It's only because I am making thicker the grid and thicker just using the evaluator more often to get the shape I want, to get the refinement of the shape I want. So you can really obtain effects or everything, calculate the shape, make your visualization, and then change the way you want. Okay, you have it, you can play around it, you can look at the code and make your own modification. And okay, that's Bezier basically. So what you have to do, the only difference here that you have to use GL map to F. And of course you have to double the set of parameters, because then you have the set for U. So it's a 4 degree with points which uses 3 coordinates. And then it's V. Actually, the trick here, yes, now remember, this is called the stride. You see, 3 and 12. Actually, this means you have U from 0 to 1 in a 4 degree Bezier curve, Bezier surface, and you use a stride of 3. A stride means that the first point will be at 0, then you have to start 3 values, 1, 1, 2, 3, and you have the next coordinates. 1, 2, 3, and you have the next coordinates. But on the other side, when you're doing V, which is the other dimension, still is defined, the values are defined from 0 to 1 of the parameters. But the control points, still that part of the curve is of the 4 degree, but the control points for V have a stride of 12. It means that you start from here, then you have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and you get the other control points. So it's like this. See, it strides like this. Because you have, it's a grid that defines the point. You have to define the direction for U and the direction for V in your matrix of points. And then, of course, you need 2 loops to make the 2 orders of the curves, cross them, and form a surface. Then we have NURBS. Well, NURBS is actually B-splines. The only difference is that with NURBS, you have also the possibility, if you want, to specify a 4th coordinate, which is the homogeneous coordinate, which makes the curve rational. Rendering the curve as rational allows you to close the curve and make circles or ellipses. But imagine that it is, okay, it's a B-spline basically. So B-spline NURBS, it's non-uniform rational B-spline. What you have to do here is that you can change the curve control points, which are these over here. So you change them. Okay, so you still make a curve. You don't see much of a difference here because, well, the degree is kind of the same. That's a pity here that I don't have the possibility to elevate the degree in order to see a different behavior. That would be welcome if one of you or a group of you would provide me this possibility. What you have to do is not only provide the control points, but you also need the knots. Here you see, actually I'm quite blocked because if I want to make a clamped B-spline, here the system just gives me 8 knots. So I have a curve of degree 8 minus n, which in this case is 3, minus 1. So it's 8 minus 4, so it's a degree 4 B-spline. Because it is a degree 4 B-spline, I need 4 knots to 0 and 4 knots to 1. And this means that I have no knots left available to subdivide the curve. So actually, to make a decent example, I would need something a little bit more complicated. Let's see if I have something. No, the surface also is not actually quite as much, but okay. Oh, this is busy, I'm sorry. No surface. Well, okay. Actually, drawing a NURBS is simpler. I can show it to you on the slides. You have them. So this is Bezier. We have seen. Use map. In map, you just have to know the order, the stride, which is the number of cells, values that I have to jump in my array, and the coordinates of the control points, the matrix of the control points. Then you can have 1 point every time you do GL eval. Gives you 1 point, which means that if you want all the points, you have to loop over the number of steps you need to create a curve. If you want to make a surface, you don't need the monodimensional evaluator, but you need the bidimensional evaluator, which is map 2D, and you need to provide 2 sets of parameters for U and for V, which is the two input parameters. And of course you need 2 loops. For NURBS, what you have to do is define the array of control points, the array of knots, then you define the NURBS surface. Well, first you define a little bit of properties, like sampling, tolerance, the display, for example, outline polygon, a callback method to catch errors from the NURBS if you want. And then you need, this is the idea in which you do the rendering, you don't need to do a for loop. You just do a begin surface, giving the NURB that you have declared here with glue new NURBS renderer. And then you define the parameter of the surface with glue NURBS surface. And you just pass the number of knots, the array of knots, the evaluator itself. This is for the 2 dimension because this is a surface. And then you have the control points, the number of control points in both directions. And then you end. As you do begin surface, you also do end surface. In this case, I use the same knot vector for U and V with a surface order of 4 to make a matrix of 4 by 4. That's the example. Okay. You are welcome to see the source itself and experiment with that. Okay, I would say it's enough for curves and surfaces. And I would like to introduce a different topic, which is the topic we should have introduced today. We are still lagging behind of half a lecture, actually. And it's a method for collision detection. As soon as I find this set of slides is related to a problem which is common when you are making computer graphics simulations or visualization in which you have, well, a degree of interaction with the user, which either is moving objects around or moving his point of view inside the scene. So, for example, it could be a game, or it could be a medical visualization, or a CAD visualization. The point is, what are the best techniques to detect when a specific object or the viewer is touching, colliding with another object in real time and during movement. So, for example, it's a, I don't know, car racing game, and you want to know when the user which is driving the car is going against a rock, whatever, or a building. So you need to detect in real time the collision between the volume which is represented by the car and the volume which is represented by the rock or the building. This is actually called collision detection. Or you have another application which is, well, you know, when your viewer is actually not represented on the screen, but you have a 3D personal visualization. And for example, you see on 3D stairs, or a slope, or a hill, and your character or your user is going down the stairs or down the hill, and you don't want the representation to let him think that he's floating in the air. You want him to feel gravity and go down the stairs automatically. That's an application of collision detection, which is called terrain following. That is, detecting the collision of your character with the terrain at every movement, and determine if you don't have collision anymore, and bring back your representation to collision. That is, follow the profile of the terrain following. So in either case, to implement those things which are necessary if you want to convey to your user a feeling of realism. So if the simulation has to have a meaning to the user that it's using, the user expects to see collisions where he expects them. I mean, you cannot think that things are compenetrating, otherwise your simulation or your representation is not convincing, or even it starts to get confusing. So you need to give that kind of feedback. We will consider some techniques. In some cases we will go in full detail. In some cases we will just give a few hints, because after a while it starts to get complicated. There are actually the following techniques. Detect a collision of a sphere against a plane. That's the simplest collision. Of a box against a plane. And these are two cases of environmental collision. Very often, when you're checking the relationship between the object and environment, for example, in terrain following, what you do is sphere plane or box plane, where the plane is usually the terrain. So you can easily approximate the stairs as a plane, and then make more or less your character checking, represented as a sphere or as a plane, checking the collision against, as a sphere or as a box, checking the collision against the plane which is approximating the stairs. So this kind of terrain following is also called environmental collision, and it is usually done by checking the collision between a sphere or a box against the plane which represents the environment. The other family of collision detection problem is when you want to check the collision between two objects, possibly between two moving objects. So it's like two cars crashing one against the other, both of them moving. And that you can do using sphere against sphere or box against box. It's up to you. Well, of course, box against box is the most complicated of the two. Sphere against sphere is the simplest one. Well, let's see the approaches that we can use to solve quickly this problem geometrically. As you might imagine, these are heavily related to the problem of determining the visibility of a bounding volume against a Frusta plane. Do you remember that we have been discussing that? So the idea is to apply the same methods, but we have an added complication, which is the fact that at least one of the two movements has velocity, meaning that one of the two objects is moving. So we need to determine if applying a velocity to a specific point of the bounding volume, we will detect collision at a certain point. Consider a sphere S, which is in contact with a plane L. So you remember that the plane is actually described as a vector with 4 elements. 3 elements being the normal to the plane which I'm describing. This sphere is contacting the plane being on the positive side of the plane. And there is a P, which is the center of the sphere, and the distance from the center of the sphere to the plane is R, which is equal to the radius of the sphere. So therefore, the scalar between L and P is R. We knew that already, because if we shift the plane by R along the direction of N, that is N and the last element D minus R, then we have that P belongs to the shifted plane and L scalar P equals to 0. Okay? That's the test that we already know when we are checking visibility determination of a sphere against a Frusta plane. So the same thing. What do we add here is that we imagine that the center P has a velocity attached. So it's moving with such a speed that the center is in P1 at the time 0, and it is in P2 at the time 1. We imagine that initially there is no intersection with the plane L, and the center lays on the positive side of L, so in this area of the plane. If you have that L scalar P2 greater or equal than R, then until t equals to 1, there has not been any collision. So it's easier, because given what we know, it is just a matter to check in any instant the position of the center of the sphere against the plane with which we are checking the collision. Until we have that this scalar is greater than the ray of the sphere that we are considering, then it means that we don't have collision. Because we will have collision only when L scalar P equals to R. This one over here. Okay? We've seen that, I think, 1 month ago. So this is the concept. I have to write a movement equation which tells me, if I put into this kind of problem the velocity vector, gives me the information of if there will be a collision or not, and if there will be, when, at which point of time. That's easy, because I know I can very easily determine the velocity, because I have one point at one time and another point at the other time. So if I suppose that I have a linear velocity, so there is no acceleration, very easy, P2 minus P1. This is my velocity vector between 0 and 1. Then the trajectory of the center can be interpolated as a line between the two. So it's a few approximations, of course. And this is the trajectory starting from P0. I mean, in time 0, I am in P1, and going ahead with time, I am following the velocity v, which is actually the difference between P2 and P1. I have to check if within 0 and 1, is there any value of t for which, well, the shifted plane, which is this one, scalar, the position of the center in relation of time, equals to 0. That would mean that I have a collision for that certain value of t. So I have the idea. I just start messing around with the equations, so just basic stuff. This is my condition. Translated L multiplied by the motion equation of the center of the sphere has to be 0 if I want to check the collision. But the motion equation of this is P1 plus T LV. I did this because I'm already multiplying the scalar, which has the associative property, to both of the terms. Doing this, I am able to extract T, and this is the equation to check what is the T in which I will have a collision. You can already see that for a velocity vector which is parallel, well, perpendicular to the normal, this contribute over here goes to 0, right? Because the scalar in this case between V, which is perpendicular to L, which actually contains n, which is the normal, will go to 0, and therefore this will put time to the infinite. This is correct, because if I have a velocity vector which is perpendicular to the normal, to the plane, it means that my sphere is running parallel to the plane. And it means that collision will be only at the infinite. So that's correct. Otherwise, if I have a solution for t between 0 and 1, it means that I have a collision. Be careful that that time, if you use that time to calculate the position of p at the time of collision, what you have is not the point of collision. It's the position of the center at the time of collision, which is not the point of collision. The point of collision is C, which is the position of the center of the sphere at the time of collision, minus R multiplied by N. Why minus? Because I'm getting crazy like this. Why minus? Because okay, thank you. Okay. Let's take the other one. Okay, N is this way, right? This is the time of collision. This is the point of collision, see? At the time of collision, this is the position of P dt, P of t, over here. But to find C, I have to sum the position of P plus minus Rn. Why? Because I have to go this way, you see? To go from P to C, I have to go in this direction, of which quantity? Of the quantity R. R gives me the length of the vector that I have to subtract from P. But the direction is the same of N with the opposite. So it's R multiplied by minus N. Of course, N should be of unit length. Otherwise, this doesn't work. You see? So it actually means take P and go down of R in the opposite direction of the normal. This is what the equation means. In order for this to work, you have to take care that this n is pure direction. To be pure direction, it means that you have to be careful that the norm of n is 1. In this way, it will be a neutral element in this multiplication. Okay? So, this is the position of the point, P in the time of collision minus Rn. So, be careful that if in the exam you will find calculate the point of collision, this is not the center of the sphere. It's the point of collision. Okay. Okay. Let's do box. The idea with box is pretty much the same, but the problem with the box, as we had with the visibility determination, is that the box doesn't have a radius. That's no problem. That's not a problem because we use the concept of effective radius. This one over here. The only thing about effective radius is that the effective radius is dependent in every instant from the mutual position between the natural axis of the box and the normal to the plane. So, therefore, you can calculate the effective radius, but you need to know the orientation of the box, R, S, and T, and the orientation of the normal, N, first. Second, if the box is going down always with the same position, that's fine. You calculate the effective radius once, and then you can apply the velocity over the center of the box and do basically the same thing that you did with a sphere. But the real pain in the ass is if the box is not only moving against the plane, but is also rotating or spinning. In that case, you need to know the instant effective radius in relation to the rotation. We don't have it here. But you could, well, easily write an effective radius dependent on time and dependent of the rotation. You need to know the rotation, the motion equation of the rotation, and plug it in to calculate the effective radius. But it can be done. This is one problem, that because the effective radius changes, you have to take care of what will be the collision. You can also say, okay, I try to do without, even if it is rotating, I don't care. Let's consider that it is not rotating and approximate it more or less. It could also be feasible, it depends. Okay? If you're writing a game for, I don't know, well, a small computer, you don't care. But if you're actually doing something, I don't know, scientific simulation or something military where you need precision, then you can hardly do that kind of approximation. You need precision. You have to be aware of that. That's one problem. The second problem is that with the sphere, once you know what is the position of the center at the time of contact, it's very easy to determine the point. With the box, you have several cases of contact, which depend on the orientation of the box. You can have, for example, 4 points of contact if the box is contacting the plane with one of the faces. You can have 2 points of contact, well, 2 vertices of contact if it is contacting the plane of one of the sides. And you can have 1 single point of contact if the box is contacting in one of the corners. You see? So, that's not trivial. I mean, it should be actually, it's not just a matter of finding one point of contact, but of finding out how many points of contact you have. So, how do you solve that problem? First thing, you have to determine if you are going down, if you are going to land on the plane with your box with 4 feet, 2 feet, or 1 foot, so to speak. How do you know that? Well, you check how many of your natural axes for your box are parallel or not parallel to the plane. If you have 2 of the main axes, well, let's follow the slides. If you have all 3 quantities not 0, so you have none of the 3 axes parallel to the plane, that means that you are going down with 1 foot, right? Because here you're not parallel, here you're not parallel, here you're not parallel. So it will be 1 corner, because the box is completely oblique, diagonal, according to the plane. So how do you know parallel or not parallel? Well, you know that. You do a scalar product. You do a scalar product between the normal to the plane against which you are making the collision and R, S, and T, which are the real natural axes. So if R scalar n not 0, S scalar n not 0, T scalar n not 0, you are going down 1 foot. This is actually the most simple case, because then you can find the point of contact by looking for the vertex which is the most, well, the furthest down in coordinates. You don't see anything, but because I think it's very, sorry, video lab, video, it's rather dark, so I'm going to switch on a light. Okay, that's better. The idea is this one. That you have a plane. This is the plane against which you're checking collision. This is its normal. If you're going down 1 foot, it means that you are in this situation. Seleziono video. Ho selezionato video, ma non si vede più sul proiettore. It's because we are recorded for the future video lab. Video. Usually it works. Non so che cosa fare, perché qui ho selezionato Video Lab. Qui ho selezionato video. Oh, ok. Adesso sì? No? E allora devi venire giù a aiutarmi. È il mio angelo custode. Okay. In the meantime, while we are waiting for my angel to come, I'm throwing a box and I'm going down 1 foot. Okay, this one is R. This one is S. And this one over here is T. You see it? These are the 3 real axes. We are in such a situation that S scalar n is not 0, R scalar n is not 0, and T scalar n is not 0. So it means one foot down. Because we know, gentlemen, please your attention. Because we know R, S, and T not only in their direction, but also in their length, we could, do you remember that we had those equations? We could determine the center of the box, which is Q, somewhere over here. And this Q is actually the one that we are tracking over time against velocity. When we are performing the equation with the effective radius, we find